Welcome to Module 20, Applied Case Studies and Engineering Workbook. This module brings the course together. In the field, problems are rarely complete, clean, and single system. A humidity complaint may involve airflow, coil performance, ventilation, controls, and building pressure. A comfort issue may involve sensors, actuators, hydronics, sequences, and commissioning. In this module, you will practice using the complete engineering method. Define the problem, gather evidence, run defensible calculations, test the sequence, evaluate failure behavior, verify in the field, and document the decision. The goal is not to guess faster, the goal is to think clearly and make decisions you can defend. By the end of this module, you should be able to approach incomplete field problems with a disciplined engineering method. First, frame the problem clearly. Identify the symptom, the affected people or process, the constraints, and what evidence is missing. Second, use defensible calculations. That means units, boundaries, ranges, and reasonableness checks. Third, connect systems instead of treating every issue as a single point. Fourth, verify failure behavior. What happens when a sensor fails, a valve sticks, a fan trips, or a space goes out of range? Finally, document the decision so another professional can understand the logic. That is what turns experience into repeatable engineering practice. This roadmap shows how the module moves. We begin with case intake. What is the real problem and who is affected? Then we build an evidence map. BAS points, trends, drawings, sensor locations, field measurements, and maintenance history. Next, we run calculations, not to create paperwork, but to test the story. Then we review the sequence. Does the logic match the design intent? Are overrides or reset strategies hiding the problem? After that, we test failure behavior and commissioning verification. The learner will use this same method across multiple cases. The goal is to create a professional habit. Do not jump from symptom to set point change. Build the evidence trail first. In the real world, we rarely receive a complete problem statement. We receive a complaint, an alarm, a trend screenshot, or a system that is not behaving as expected. That is only the symptom. The professional job is to convert that symptom into evidence. We ask what can be verified, what is assumed, what measurements are credible, and what data is missing. Then we use a method to move from uncertainty toward a defensible decision. This is especially important for multi-system problems. A room that is too warm may not be a thermostat issue. It could be airflow, hydronics, a sensor bias, a valve problem, a sequence conflict, or a scheduling condition. This module teaches the discipline of staying with the evidence until the physical story makes sense. This is the complete engineering method we will use throughout the workbook. Start by defining the problem and the system boundary. Then gather evidence, trends, drawings, field measurements, point lists, alarms, and observations. Next, calculate. Use the equations that match the system. Airflow, heat transfer, hydronic flow, pressure, electrical load, or moisture balance. Then test the sequence. Does the control logic do what the narrative says? After that, verify failure behavior. What happens when the sensor fails, when a device is in hand, or when a critical alarm occurs? Finally, commission the result and document the decision. A good engineering workbook should allow someone else to follow the same evidence and understand why the decision was made. Case 1 begins with a familiar complaint. The spaces are close to temperature set point, but people say the air feels sticky. This is a classic situation where the first visible BS value, zone temperature, is not the whole story. The missing evidence is usually moisture-related, room dew point, coil leaving dew point, outdoor air humidity, airflow, supply air reset behavior, and reheat operation. The workbook task is to build a psychrometric evidence map. Before lowering zone set points, ask whether the coil is cold enough to dehumidify, whether airflow is too low for moisture removal, whether outdoor air moisture is high, and whether reset logic is sacrificing latent performance. The professional decision rule is simple. Do not solve a humidity problem by blindly lowering temperature. Verify the latent load path first. This slide shows the workbook path for the humidity case. First, define the boundary. The air handler, mixed air section, cooling coil, VAV zones, outdoor air, and any reheat path. Second, gather trends. We need outdoor air temperature and humidity, mixed air, leaving air, supply air, zone dew point, airflow, and reheat status. Third, calculate the air side story. Is the coil cold enough, and is there enough contact time to remove moisture? Fourth, review the sequence. Supply air reset, economizer enable, VAV minimums, humidity overrides, and reheat limitations. Finally, verify the result. The decision is successful only if dew point, complaints, and coil leaving conditions improve together. The workbook is not extra paperwork. It is the thinking path. Case 2 is a hydronic problem. The pump is running hard, but the plant is not transferring heat efficiently. The most visible symptom may be low delta T, but that is not a root cause by itself. We need to ask physical questions. Is the system moving too much water through too many coils? Are three-way valves bypassing? Are control valves oversized? Is the differential pressure sensor in the wrong place? Are coils loaded lightly because airside conditions are wrong? The calculation Q equals 500 times GPM times delta T gives a practical check, but the calculation is only useful if the flow and temperatures are credible. This case trains the learner to connect hydronic physics, valve authority, differential pressure reset, and plant energy before making a control change. Here is a sample calculation. The plant is moving 900 gallons per minute with a chilled water delta T of only 6 degrees. Using the field formula, Q equals 500 times GPM times delta T. That gives about 2.7 million BTU per hour, or roughly 225 tons. Now, the professional question is not simply whether the formula is correct. The question is whether the result matches the rest of the system story. Does the chiller report a similar load? Do the air handling units show a matching load? Are valve positions high or low? Is airflow normal? Are there bypasses? Are the flow and temperature sensors credible? The calculation is a filter. It helps separate possible explanations from physically inconsistent ones. Case 3 focuses on critical spaces such as isolation rooms, labs, clean rooms, pharmacies, operating rooms, and other pressure-controlled areas. A pressure alarm cannot be evaluated by the pressure number alone. We need to understand the room function, the reference location, the supply airflow, the exhaust or return airflow, transfer air, leakage, door position, wind, and stack effect. A pressure sensor may be accurate, but referenced to the wrong location. A room may meet pressure when the door is closed, but fail when the door opens. An alarm may be too fast, too slow, or tied to the wrong operational state. The workbook method requires the learner to map the airflow relationships before tuning a loop or changing alarm delays. This slide introduces failure behavior. A design review is incomplete if it only asks whether the system works under normal conditions. We also need to ask how it fails. If the pressure sensor is lost, does the room alarm, freeze, or drive a fan to maximum? If the exhaust fan fails, does the space lose containment? If a door opens, does the alarm respond appropriately without creating nuisance alarms? Can an operator override defeat a protective relationship? The workbook requirement is to identify the safe state, alarm priority, and operator response for each failure mode. This is where BAS engineering becomes risk management. Case 4 connects sensors, actuators, valves, dampers, and process response. A controller command is only the request. The actuator must move. The linkage, stem, shaft, valve, or damper must translate that movement. The position feedback may confirm travel, but even feedback is not the final outcome. The real question is whether the physical process changed: airflow, water flow, temperature, humidity, pressure, or equipment operation. The workbook asks the learner to verify each link. Is the command correct? Is the actuator receiving it? Did the device move? Did the process respond? Did the outcome match the intent? This protects us from replacing controllers when the issue is linkage, or replacing valves when the issue is a measurement assumption. Design review is not a paperwork exercise. It is a relationship review. Equipment selection matters, but it is only one part of the system. We also review measurement quality, sensor type, location, range, units, calibration, and reference. Then we review the control sequence, intent, reset logic, overrides, alarms, and safeties. Next, we review failure behavior. What happens when critical devices or measurements fail? Finally, we review commissioning. What tests prove the system operates as intended, and what trends must be captured? This checklist creates a repeatable review process. It helps the team catch problems before they become expensive field failures. A recommendation is not complete until we define how it will be proven. The commissioning plan begins with a baseline. Capture the trend, the field condition, the current sequence behavior, and the complaint or alarm pattern. Then test carefully. Where practical, change one controlled variable at a time so the result can be interpreted. Next, verify the process response. Did temperature, humidity, airflow, pressure, energy, or alarm behavior improve? Did any safety or operating limit move in the wrong direction? Finally, record the result. The most important professional habit is to define acceptance criteria before the field test begins. Otherwise, the team may see what it hopes to see rather than what the system actually did. The workbook deliverables are intentionally practical. For each case, learners submit a problem statement that defines the affected spaces, systems, people, risks, and constraints. Then they create an evidence table. This includes BAS points, trends, drawings, field measurements, maintenance history, and assumptions. Next comes the calculation page showing formulas, units, ranges, and reasonableness checks. After that, the learner reviews the sequence: design intent, actual behavior, overrides, interlocks, and alarms. Finally, the workbook includes a commissioning record, test method, acceptance criteria, results, and the final decision. This is exactly the structure that supports professional communication in the field. These are the most common mistakes in multi-system problems. The first is changing set points before defining the system boundary. The second is trusting a trend without verifying sensors, units, and scaling. The third is using design values as if they were measured values. The fourth is ignoring failure behavior and safeties. The fifth is documenting the final answer without documenting the evidence. These mistakes are understandable under time pressure, but they lead to repeated problems and weak decisions. The professional habit is to slow down the diagnosis so the corrective action can be trusted. In a complex building, disciplined thinking is not slower in the long run. It prevents rework. Let's check understanding. The scenario includes humidity complaints, low chilled water delta T, and VAV low airflow alarms. One operator wants to lower zone set points and raise duct static pressure. That may feel like a fast response, but it does not address the multi-system nature of the problem. The best answer is C. Build an evidence map across air, water, moisture, sensors, and sequences before changing the control strategy. The issue may involve supply air reset, coil dehumidification, airflow measurement, valve behavior, hydronic flow, outdoor air moisture, or a unit conversion problem. The workbook method keeps the team from solving one symptom while making another worse. This module closes the engineering workbook by reinforcing the professional method. Incomplete problems are normal, but guessing should not be normal. The workbook creates accountability by documenting assumptions, evidence, calculations, units, trend windows, sequence behavior, failure response, and decisions. We also learned that systems interact. Air, water, electrical systems, controls, sensors, actuators, building envelope, pressure, and moisture can all be part of the same problem. Failure behavior matters because buildings must remain safe when equipment or measurements fail. Finally, every recommendation must be commissioned. Define what success means, test it, trend it, and document the result. This is how BAS professionals make decisions that are practical, defensible, and valuable to the building owner.